All right, today we talk about slope fields, and you should have a notes package in front of you. It looks like this. That's very thick. Yes, very thick. Okay. So a slope field. Now, we talked about slopes, and we talk about a field. It's not a field like a farmer's field, but instead a field is like an area, okay? So we are going to discover what slope fields are. They are pictorial representations of all possible solutions to a given differential equation, all right? So a pictorial representation, which we're going to be working on today, of all possible solutions to a given differential equation. Now we talked about differential equations yesterday, last day. A differential equation, like you see down here, is simply an equation that contains a derivative. So dy dx equals x plus 3. That's a differential equation. Okay. Now, so remember that a differential equation is the first derivative of a function. Thus, the solution to a differential equation is the function f of x. Now, let's pause there for a second. So when we're talking about differential equations, if we were to solve a differential equation, then what we're trying to do is we're trying to find the original function for that derivative, right? Again, we did this yesterday. We're given a differential equation, and we're asked to solve for the either general solution, which would be the antiderivative of this function, or the particular solution, which is involving some initial conditions to find out what plus c actually is. So we did that yesterday. Now, this slope field will be a pictorial representation of the solution. So the solution to a differential equation is the function f of x, or just y. And we are now doing a pictorial representation of the possible solution. So we're going to a pictorial representation of the original function f of x, but not just one, but all of them, all of the possible solutions. There is an infinite number of solutions to any differential equation if you are not given initial conditions. Okay, so show your work and explain why. Well, let's do that together. So if we have something like this, dy dx is x plus 3, basically to solve this we want to find out what y is. Okay, well this is the derivative, so we need to take the antiderivative, or we need to integrate with respect to the variable. So integrate with respect to x here, both sides. So that will give us y on the left, and this would give us 1/2 x squared plus 3x on the right. But because we don't know any initial conditions, we actually don't know if we have a plus 5, plus 7, minus 3.2. We don't know what it is. So we have to put the plus c. This should be ringing a bell. Ringing a bell? Okay, good. No? Okay. I heard a yes, and I think I heard some animal noise back there. We're not, okay, no zoo today. All right. So this is the general solution, which the pictorial representation that is the slope field is the solution, but it's including all of the possible solutions. So we are pictorially representing this right here. All right. Now, how do we do that? We're gonna get to that in a second. Okay. But first of all, I want you to complete this on the bottom. Just looking ahead, why are we studying this? Heads up to the AP exam. You're going to be expected to do the following things with slope fields. You're going to have to sketch a slope field, which we're going to get to right away. So you're going to have to sketch a slope field given a differential equation. It's the first thing we're going to do today. Second thing, given a slope field, you are going to draw or sketch the graph of the particular solution given initial conditions. So again, I'll just give you a minute to write this down so that when we travel through this lesson, you're going to come back to this and say, oh yeah, I've done that. I know how to do that. And you can kind of self-check here as to kind of what you understand here. So given a slope field, to draw a particular solution. And we're going to do that possibly today as well, maybe next day. Match a slope field. So we're going to match slope field to a differential equation. And finally, number 4, match a slope field to a solution of a differential equation. Okay, I want to first draw your attention, before we actually draw or sketch a slope field, think about other kind of fields that you've heard about, a gravity field perhaps, or a magnetic field. Here on the screen you can see are some pictorial representations of magnetic fields. So notice, oh, I'm frozen still, sorry. Now you can see on that screen there. So these are pictorial references for magnetic fields, and you can kind of see how the forces, the magnetic forces, sort of interplay with each other, the north and south poles. And if you had, you know, metallic particles that would respond to the metal fields, you would have something like this. And this right here is a very close sort of situation as to what we're going to try and sketch. We're not going to be doing magnetic fields. We're going to be doing slope fields of differential equations or solutions to differential equations. But there's going to be a lot of similarities. So I'm just going to quickly grab a quick sketch here and bring it into our notes so we can compare this. Okay, come on now. Here we go. So this is page 2. And let me just put a little picture of our slope field somewhere. Okay, maybe here. There we go. Okay, so that's our magnetic field, and the slope field is something we're going to kind of create something that looks a little bit like this. Now, how we do this is we have to take a look at this differential equation, and what we're going to do is we're going to try to sketch what the derivative might look like at various points in the field that is the coordinate plane. Now, what's one interpretation of a derivative? A slope of a tangent line to any part of a function. Now think about it. The function would be the solution. So what we're going to be graphing, what we're going to be sketching, are tiny little pictorial representations of tangent lines to all possible solutions. And how we do that is this, okay? So what we have to do is look at the differential equation and understand that this is the description of the slope of the tangent, okay, at x. Now this differential equation only contains the variable x. That's great. This is going to be real easy, okay? So these points serve a purpose. We are going to sketch a tiny little tangent at each of these points. And the tangent, slope, is going to be described by this right here. In this case, x minus 1. So let's start at the origin. Okay, we're going to start at the origin. And again, I'm going to be drawing little tangent lines. Notice on the right here, you can kind of see that this slope field is sort of built on these little lines. You see, I could sketch these little lines, just like hairy little lines, and this is what the slope field would sort of comprise of. You see that? So you put all those together, you get the little bit of slope field. So that's what we're going to do. Now, if x equals 0 at the origin, then the slope of the tangent line at the origin would be 0 minus 1, or negative 1. So what I need to do is I need to sketch a tiny little tangent line, or a little section of a tangent line, at the origin that has a slope of negative 1. So notice that 1 unit over 1 unit down. So if I draw a little line like this, that's going to be the very first addition to my little slope field here. Okay? So you see how that slope of that little tangent line is negative 1? Okay? Now, what other points have x value of 0? Well, all of these points in the vertical or on the y-axis, right, have x equals 0. So guess what? At this point right here, the slope of my tangent line should also be negative 1. And at this point, 0, negative 2, what's the x value? Well, it's still 0. Now, how accurate do these have to be? You should try to be as accurate as you can, in a sense that you see this is definitely between this point and this point is a slope of 1. So make your point kind of like, you know, in line with those 2 points. So yeah, you're going to want to be fairly exact. And I've got a negative 1 here too, negative 1 here too, or here as well. It's really tough on my tablet to make these exact, sorry. Okay, so you see how we've started there? Yeah, you good with that so far? All right. Now, let's move to x equals 1. All right, so if x equals 1, then we have 1 minus 1. The slope should be 0. So wherever x is 1, we should have a horizontal slope. And so x equals 1. At all of these points, x equals 1. And they're all going to be the same in the vertical column because guess what? There's no y value affecting what the value of the slope is. As the y value changes in some other examples that we do, like, maybe this one, it's the point x, y both contribute to the value of the derivative, right? So this one's just x is our only influencing factor here. Okay, so if x equals 2, and again, I'm just going a little faster here now, x equals 2, then our slopes, our little tangent slopes on our slope field are going to be 1, right? So now positive 1. So you can go on all these lines and positive 1. All right. Okay. All right, so let's continue with negative 1. That's going to be a negative 2 slope. And how do we do that? Well, look at this. You could take any point and go down 2 over 1. So you want to draw a line that would connect those 2 points right there. So I'm trying not to mess this up too much, but it's just going to be a little steeper here. Okay, negative 2 as a slope. And then finally, if x equals negative 2, we have a slope of negative 3. Okay, so down 1, 2, 3, and over 1, again, just a little steeper. So it's going to be the best you could possibly do here. I understand if it's a little bit tough to distinguish between a slope of negative 2 and negative 3. I understand that. But this is what you kind of want to end up with. Okay? That's what you want to end up with. Now, let's go back to the concept of a slope field. And I just want to go back to this very first page where we said that this is a pictorial representation of all of the possible solutions for a differential equation. And so if I now go back to this particular example, we could find out what the general solution is here. And I think I'd like to do that. So for example, if I were to take the derivative of both sides, which you don't have to do, but in order to explain this to you, I want to show you this. So you take the integral of both sides, I would get y equals 1/2 x squared minus x, right? So this would be a parabola plus c. This would be a parabola that opens upward. It's a little bit wider than normal, okay? But one of the possible solutions, okay, if you bear with me, one of the possible solutions could look like this. It could be a parabola that looks like this. It could be a parabola that looks like this. Or a parabola that looks like this. And what I want you to see is that anywhere where I draw these possible solutions, do you see how the graph kind of like fits in with the slope fields? Okay? So these are the graphs that are the possible solutions, right? I'm just kind of drawing all of these possible solutions. And the slope field sort of accommodates all of these possible solutions. And as this continues on, it gets steeper and steeper. That's why the slopes, as you move left away from the origin, they get a little steeper, don't they? Because that parabola would continue to go up, and all the tangent lines would be steeper. So these are, all of these little parabolas would be all the possible solutions. And so we can't draw every possible little tangent line, or else it, it would look more like this picture over here, right? So we just want to graph the little tangents at each sort of point where it would cross the lines on a grid, okay? Okay, any questions there so far? So if you blur your eyes a little bit, you could probably see that inside this slope field, you would be able to spot a parabola. Do you see how a parabola would sneak right in there, in between all those lines? Oops. Did that just disappear on me? Oh, great. Thanks a lot, modern technology. Okay. All right, so that's the slope field you're looking for, and let's see if I can get rid of this. Okay, let's do another one. Let's do one where x and y both contribute to the slope field. That's the next problem on your page. Okay, well, now we're looking at points both x and y. So if I do the origin, 0, 0, I'm going to have 0 minus 0. That's going to equal 0. So I do have a flat horizontal line on 0. Let's move up. Let's take a look at the point 0, 1. So does that change things? Yeah, it does actually. The value of the tangent line is going to be now 0 minus 1, or negative 1. So as we move up, this one now has a slope of negative 1. So 0, 2 is going to be 0 minus 2, or negative 2. So as we move up, looks like the slope increases, and this is going to be negative 3. That's interesting now. Now, how you place these, it doesn't really matter. I like to go in vertical columns sometimes, but you can go diagonally. If you see a pattern and you know, hey, all these slopes are going to be the same on this diagonal, then go ahead and do that. Like, for example, what about 1, 1? 1, 1. Well, 1 minus 1 is 0. What about 2, 2? 2 minus 2 is 0. So guess what? I know that on the diagonals, where on the y equals x line here sort of thing, those are all going to be zeros. Right? Negative 1 minus negative 1. Negative 2 minus negative 2. Give me all 0. So how you place them doesn't matter, but you just want to make sure that every dot on this, you have the appropriate little tangent line. Okay. You guys get the idea there? Okay, 1, 0. Well, 1 minus 0 is going to be 1. Okay. 2, 2, 0. Well, 2 minus 0 is going to be 2. And so on. So I'll tell you what, I'll give you a few minutes because you might be working on a different point than me. So go ahead and take a minute to finish this. I'll do the same. All right, so this is what your slope field should look, something like this. Now, this is going to look strange, right? You're saying, oh, a parabola doesn't fit in there. Nope, because the solution to this differential equation is not a parabola. As a matter of fact, it gets a little bit tricky when we have x and y. We haven't done that yet. So this is going to be something called a separable differential equation that we'll do in the next sort of section. But the reason why we can't just go ahead and solve, that we just can't go ahead and solve like we did up here and just say, hey, this is our general solution, so it's got to be a parabola and that works. You can't always do that. It's not always easy to do that. So anyways, yeah, it should look something like this. And the possible solution, you can kind of see what a possible solution might look like. It's interesting that right here, these slopes are all positive 1. They're all positive 1. So that's going to be probably some kind of oblique asymptote. And you might have a graph that looks something like this. You might sneak in like this, and then come in here, and then go 0 like that, and then boom, skate away like that. So it could look something like this. There also could be another arm to it, right? This could be this whole thing. Let me see if I can do this. See how fancy I can be here. So this graph, I'm not going to be able to pull all those arrows, but if this slid down here, it could be this graph too, right? So it could be all the way down here. It could look like this. Well, right? Something like that. And you could possibly have another arm that would still make this a function. Nah, you couldn't here, I guess. So it could be above, it could be maybe below, I don't know. It could be something down here as well instead. We don't know because we don't know much about the initial conditions, so I'm going to just put that back where it was. Actually, I'll erase it. But you kind of see how the solution could fit somewhere in there like that? Any questions? This is going okay? All right, let's flip the page then in your notes. Given a slope field, sketch a solution curve through a given point. So here's where we have a slope field that's given, and we have, look at this, we have some initial conditions right here. All right, so 1, negative 1, 1, negative 1. Right here, this is a point that's on the graph. This is actually on the graph. So this is very similar to one of the ones we did earlier. This looks like a parabola might fit in here. And guess what? This is not going to be the parabola that is the particular solution. You see that? That's not going to be it. Why? Because it doesn't go through this point. But hey, could this be the particular solution right about there? Yeah, that looks really good. So that is going to be your particular solution. So that all of the little slopes that you've graphed in your slope field, or slopes that would meaningfully be in between there, would actually be, you know, slopes that fit on your parabola, on your actual function. You see that? Good? All right. So again, this is pictorial. We've solved differential equations algebraically, or I should say mathematically, in the numerical way there. This is graphical, so slope fields are very graphical by nature. Awesome. Okay. Let's tackle the next page. Matching slope field diagrams, or slope fields, to the differential equations. Okay, it's two differential equations. Now, you have 2 pages there. So you have this page that you see there, and then on the very next page is the differential equations that you're going to match up with them. Okay, so let me see if I have, I don't think, yeah, I guess I have some of these here. So let me just take the first 4. Whoopsie. What's going on? Let me just try and copy some of these over. Yeah. All right, I'm going to put these, get rid of those. Where should I put these? Okay. All right. Okay. So here's, let's take a look at number 1 first. It's over on the side of the screen there. Okay. So dy dx is sine x. Now you have to be careful. Ooh. The graph that would fit inside the slope field is the solution to a differential equation. It's not sine x. So we are not looking for sine x that would fit in here. Okay? So don't be confused. This looks like is pretty close to sine x, right? This looks like sine x there. D does not go with number 1. Okay? That's not right. Why? Because what we're trying to look for is a slope field where the solution to a differential equation would fit. So what we do is, in this case, the easiest thing to do would be to solve, because we can take the integral of sine really easily. So y should be, what's the integral of sine? It's negative cos x plus c, right? So we are now looking for a slope field that could fit a negative cosine x graph. And a negative cosine x looks like this, right? That's negative cosine. So you're looking for something that looks like this. So which one do you think might fit that bill? Okay. So I like it. So if this was, let's say, -1 down here, we're looking like, yeah, it could be.
Sorry for the interruption, but Grizzly fans, we got a lot to be excited about. So if you're on the first floor, give me a go, Grizzlies, go. Second floor, go, Grizzlies, go. Third floor, go.
Go, Grizzlies, go! All right, go, Grizzlies, go. All right, big announcement.
Sorry for the interruption.
Okay, so let's continue on here. So do you guys see that? I think I like I as well. There's the cosine, negative cosine that fits in there. So that's I. Okay, good job. Let's do number 3. Let's figure out what 3 is. Hey, the integral of e to the x, I've heard that that's pretty easy to do. What's the integral of e to the x? dx? It's e to the x, yay! Who remembers what that graph looks like? It's an exponential function. So it follows the x-axis on the negative side, and it kind of comes up through 1 and does this thing, right? So where does that look? Say B? I like it. It would fit right in here somewhere. So yeah, boom. It feels like a complicated Dora the Explorer game.
Yeah,
Is that what you're saying?
Like when you would watch it and it'd be like, can you show us where the red house is?
Hey, knapsack. Yeah. Okay. So your assignment right now is to finish this little matching game. Don't look so sad. It's going to be fun. Yeah. All right. Okay, so the integral of 2, what's the antiderivative of 2x? That's going to be x squared and plus 4x, right? And obviously these are all plus c, but focus on this, x squared plus 4x. That's going to be a parabola. If we factor that, that's going to be x times x plus 4. So we're going to have, you know, the graph, if c was 0, we'd have an intercept at -4 and an intercept at 0. So it would be a parabola that looks like this. So do you see a slope field that would manage that?
Mr. Ma,
Yeah,
could you
hey.
please go to the library?
Right here. So
Mr.
something
Ma,
like this.
Could you please go to the library?
Something like that. So 2 is going to be A, okay? Two. Yep.
Oh, because it moves that. And then
So that's dual solution there. Now, the other way you could do this is the long way. If you can integrate these functions, that's the best way to do it. That's the quickest way. But remember, what you could do is, without integrating, you could do one by one. You could just test values. So this differential equation, okay, all of the slopes would be 2. All of the slopes would be 2. Doesn't matter what x is, doesn't matter what y is. So do you see a different slope field where all of the slopes for all of the little lines are 2? J. Do you see that, guys? So that's one way you could do it too. You could just look at the derivative and find out where the slope field is. That might take a little while though, to be honest, because you might want to look for where you have zeros perhaps. I would say for G at, looks like 1, 2, 3, at x equals 3 it's 0. So can you find a differential equation where at x equals 3 it's always 0? X equals 3 is always 0? Well, 3 cubed. No, minus 3 times 3, that's not it. So looking back at it again, that actually is 1, 2. So x equals 2 is always 0. X equals 2. So if you did it that way, right here, look at this. When x equals 2, that's always 0. So at any x equals 2. So number 7 matches with this one, G. And you could test some other points too. If you tested something at, you know, about 3-ish, it should be around 1 or whatever. So there's the answers right here if you want to check your work.
You're all
Okay, so that's going to be lesson 1. We will continue. We're going to work through this package a little bit more, so we'll pick this up. We'll continue tomorrow.